In this presentation we'll look at the issues involved in using the UML and object constraint language notations as a semantic representation in the re-engineering of legacy code. So codes in languages like Python or Java or COBOL or Visual Basic, and representing those in UML and OCL as a stage towards re-engineering those legacy codes in new languages. And particularly this is an issue for older languages such as COBOL and Visual Basic, where we really need to capture the meaning of that program, what is the functionality of that program, and that semantic meaning can be captured in UML and OCL and then re-expressed using forward engineering in a new language. So we discussed the issues that can arise in doing that program abstraction to a semantic representation, what extensions might be needed to UML OCL to enable it to be used in that way, and then how those extensions can be managed in a integrated way, in a way that's consistent with the existing OCL type system and semantics. So it's very important when we do re-engineering that the new version of a program, the new version of a system is functionally equivalent, or at least it has the key functionalities that were in the original version, because businesses are concerned to migrate their systems, often business critical systems that are very important to how their business operates, migrate those systems to a modernized platform, modernized languages and modernized platforms, because the old languages like COBOL no longer have the support that's needed to maintain them. Now, in practice, the verification that's done is usually by very extensive testing. These test efforts can consist of more than half the total re-engineering effort, and the testing itself may take months to run, for example, the new system in parallel with the old system to make sure that they're doing the same thing. This is not a trivial process. In principle, model-driven engineering support for re-engineering can reduce that verification effort by using a formal intermediate representation that expresses the program semantics accurately, and then by using trusted forward engineering processes, again from a model-driven engineering toolset, to generate functionally correct code in a new language. Now, this is not speculation. It's a process that we've been using for several years now to use UML and OCL as the intermediate semantic representation. And the motivation for doing that is that these notations are widely known by practitioners, and they're well supported by tools and by documentation, books, and so on. But on the other hand, this choice of representation could be in conflict with the style of legacy systems, which are in the older languages, at any rate, they're written in a very procedural fashion. These languages originated before object orientation, and therefore there may be a clash of styles in doing that translation or abstraction. Perhaps a more substantial problem is that the legacy systems use lots of facilities that are outside of the OCL language. For example, files and databases that have no existing representation in OCL. So we have to decide how we're going to represent those facilities, either by OCL extensions or by some kind of library in the representation, in the semantic representation. Now, we don't want to change OCL. We want to still keep the same characteristics and language style of the object constraint language, and where possible, we would like to represent program language facilities by simulating those in the OCL language, rather than actually extending OCL. You want to minimize the extensions to the core of OCL, and those extensions should be things that are consistent in style and mathematically consistent with OCL. For example, the key things, the key additions that we want to add are map and function types, which are very widely relevant for languages, applications. These are things that are in modern 3GLs, general purpose programming languages, and therefore it makes considerable sense, or there's a strong justification for adding these into OCL. On the other hand, more specialized facilities such as random number generation, file handling, would be better represented as additional libraries that are optional extensions, essentially, of OCL, rather than adding them to the core of OCL, because they wouldn't be needed in many uses of OCL. Now, the re-engineering approach we have applies to 7 different source languages, ranging from old languages like COBOL and Visual Basic to more recent languages such as Java, C, and JavaScript. These all have data types of numeric and string and enumerated types, record or class types. These can all be directly represented in UML and OCL. Map and dictionary types are very widely used, and therefore we can represent those by an extension in a map type. The idea of a map type in OCL has been proposed not only by ourselves but by many other people working in the OCL community. And the semantics of maps, of course, are very well understood, and there isn't a clash with the fundamentals of OCL in adding maps. More controversially, we could need pointer types. So we could extend the OCL type system by a reference type constructor, reft, whereby for each type T there is a type of references to T, permitting indirect reference to values of type T, and also function type constructors. We want to be able to represent program statements, and so we need some kind of procedural OCL. There have been a number of proposals for such a language. Here we use a simple Pascal-like notation for assignment, declarations, sequencing, conditionals, loops, and so on. It's entirely non-controversial. Some other statements are needed to represent exceptions, and this could be done with these Java-style exception statements. Now, some things we don't want to represent directly, such as goto statements. These can be simulated by operation calls where the operation represents the code that would be encountered by a jump to the label. This leads us, in many cases, to recursively defined operations instead of gotos. Problems with languages like Python and JavaScript is that we can have implicit and typeless variable declarations. Those need to be converted to explicit type declarations in using this declaration statement here, where a type is inferred by type inference. In some cases that may not be possible, in which case we simply give it a type of OCL any, meaning the arbitrary type. Now, the operations of programming languages vary in some aspects. Most significantly, perhaps, they vary in how parameters and values can be passed, how actual values can be passed to the formal parameters of the operation. This differs from language to language. In the more recent languages like Java, JavaScript and Python, the convention is usually that numerics and booleans are passed by value, whereas effectively strings, objects and arrays and collections are passed by reference, meaning that a change to the values of these parameters within the operation persists after the operation terminates. In C, we have a slightly different situation. The record type or structs are also value types. Pascal can operations can explicitly say that parameters are passed by value or by reference, including parameters of numeric and Boolean type could also be passed as var parameters. Likewise, Visual Basic and COBOL have similar facilities to Pascal. On the other hand, UML OCL, most things are value types, and the only things that are passed by reference are objects. So there's some clash here, and we have to therefore simulate pass by value semantics of things that would be represented as classes in OCL. We can simulate that by copying the arguments of the operation. On the other hand, pass by reference of value types, things that are value types in OCL like numerics, have to be simulated by passing a reference. This is a significant motivation for having reference types in the extended OCL. It allows us to simulate pass by reference by pass by value. Another unusual feature is the idea of a generator function, and this occurs in Python and JavaScript, where operations can be called repeatedly and returning different values. This can be simulated by using an iterator. Java, of course, has many of the same characteristics as OCL and UML. It's a paradigm object-oriented language. Many of the same concepts occur in UML and OCL in the same way. There are generic classes and operations in Java. These are already represented in UML as templates. We can add them explicitly to the OCL that we use in Agile UML. Nested classes, inner classes, anonymous inner classes, these are not represented in Agile UML, but they could be simulated by associated classes. Reference types in a programming language can be simulated using the ref type constructor. Editable views are a form of aliasing and are therefore problematic. We can simulate these using an OCL iterator, or we could simulate them in a more logical fashion by using invariants to say that two variables are always related in a certain way. And we in most cases we choose to use the invariant approach as a more logical and higher level representation of editable views. Sorted collections occur in various programming languages in various forms, and again we believe that this could be added in a consistent way to OCL as new type constructors. JavaScript is a scripting language. It has a different kind of programming, of course, to a different kind of object orientation model to Java. The JSON format for object literals could be represented as maps. We can have tuple assignments in JavaScript, also in Python. We could represent those by a kind of sequence assignment in OCL. Some things, such as the evaluation of a piece of text, program text, is not represented. That's kind of meta-programming. Python has an ordered dictionary type represented as an ordered map. They have a combined form of select and collect, which suggests we could actually extend the OCL collect representation. They also actually have multiple variable iterators here. We could have x in s, y in t. That also suggests an extension to the OCL iterators. Pascal is mostly straightforward. However, it has nested procedures. We could translate those to nested classes and then simulate them by associated classes. Record types are value types. In UML terms, they're non-class data types. We need to represent them explicitly as classes that are value types rather than reference types. C, main issue with C is pointers, of course. That can be addressed by using ref types, but they would need to support pointer arithmetic, not just indirection. Visual Basic, they have a collection type that essentially is a kind of ordered map. We can simulate that, but it would be more natural to actually include an ordered map type. COBOL is a big problem. COBOL has lots of features that don't appear in modern programming languages. Aliasing is used essentially in the language, and we express that by using invariants. GoTo is widespread, and of course that has to be translated out. They have quite complex versions of sorting and other facilities. We need to have some facility to have multi-level sorting. So these are the general strategies and approaches that we use to do program representation. So core libraries like the mathematical operation, these, because of their general purpose and widespread use, we add them as intrinsic operators. But more specialized functions we add as libraries. Likewise with string functions, we add them as intrinsic operators if they're widely used and generally used, but more specialized operations are put in a particular library. Function types, reference types, sorted collections and maps, we add those to the OCL type system. We believe that these are very important things to have in a specification language in any case, quite apart from the need to represent programs. There are more specialized facilities like reflection, exceptions, file management. These are generally added as libraries. They're not aligned in many cases with standard OCL, so it would be difficult to make them a part of the core language. It would also add to the language size, make it more difficult to support. Now, we have to provide a semantics for those extensions, and this is generally possible. It can be done. We can have, for example, sorted by with multi-level sorting, assignment to sequences of variables. We can expand that out in terms of ordinary assignment. Select and collect extensions can be defined using the iterate facility of OCL. Reference types and these other extended constructors have to be defined as intrinsic extensions to OCL and given semantics in the same way that you would see in the standard OCL semantics for sequence and sorted sequence and ordered set and so on. This leads us to a extended set of collection types for OCL, whereby we have the distinctions that already exist between unindexed and indexed collections and between non-unique and unique collections, and we extend those to maps so that we have potentially at least multi-maps and ordered multi-maps, and then standard maps and ordered maps. And further, to add a distinction between sorted and unsorted collections. And if we look at sorted collections, then again we can have sorted flavors of each of the preceding collection types and map types. Diagrammatically, sorted sets are a specialization of sets. Sorted bags are a specialization of bags, but that isn't the case for the collections that support indexing, because with these collections, the indexing there's a certain degree of clashing with the sortedness, and the operations that you need for sorted ordered set then are semantically distinct from those for ordered sets, and likewise with sequences. Similarly for maps. Okay, so in conclusion, we've come up with a systematic way of extending UML and OCL to provide semantic intermediate representation for reverse engineering and re-engineering in order to represent programs from a wide range of source languages. We can't say this is universal because certain languages like functional languages, logic programming languages, we don't intend to support because they are quite a different paradigm to the procedural and object-oriented languages, but we can cover a wide range of procedural and object-oriented languages and scripting languages. We tried to minimize the changes that are needed to UML and OCL, and where changes were made, we provided the semantics for those extensions. These extensions, of course, are not only used, could not only be used for reverse and re-engineering, but they could be used for specification of other systems, of new systems, and generally to increase the expressiveness of OCL and UML.